Mr. Brolin has more than 40 years' experience in the management of technical projects and large organizations as an executive in government and industry and an independent consultant. Mr. Brolin has a B.S. summa cum laude from Tufts University, an MS from George Washington University, and a professional engineer's license, currently inactive. Since retiring, Mr. Brolin has been active in our local community, including responsibility for construction of the Unitarian Universalist Meeting House in Bridgehampton, and a member of the former chair of the Sustainable Southampton Advisory Committee to the town board. The committee has helped pass several progressive pieces of legislation leading to improved sustainability for Southampton. So we're really proud that we have him in our midst. Please welcome Mr. Brolin.
Hi. Here's what we're going to talk about today, and I'll move along as quickly as I can because there is a lot of material. First, how do we generate our electricity today? This is how. 24% of our electricity is from coal, 41% natural gas, a tiny fraction from oil. So fossil fuels are still the majority of our generation. It's down about 3% in the past 10 years or so, and renewables are up a couple of percent, with hydro, as is usually the case, being the leading renewable, and wind and solar, so that totals 15%, and nuclear is steady at 20%. Sorry. So there hasn't been much change except a large movement from coal to natural gas over the past 10, 15 years, which is good for the environment. Not necessarily done for that reason, by the way. Natural gas powered power plants are cheaper and easier to build, and natural gas has been declining in price for some time, but it's still good for the environment. Of the ones that we just looked at, these are the ones contributing to emissions-free electricity, which is what we're interested in from the standpoint of mitigating global heating. I don't call it warming because it's really heating. Most of our emissions-free electricity is from nuclear power, 58%. And then you see the other numbers there. Hydro, 29%, and the other renewables, 13%. That's something you need to keep in mind when we talk about nuclear power. You throw away nuclear power, you throw away the biggest source of emissions-free electricity. Here's where nuclear stands worldwide. 415 operating plants. The largest plants are in these, largest number of plants are in the countries noted. I don't know whether you can read it, but the US is first with 94, then France, China, Russia, Korea, and Canada. China, however, has lots of them in the planning stages, I think about 40 or 45. So they have been growing fast. They will overtake the rest of us, I'm sure, because our numbers have been anemic and actually declining over the past decades for various reasons. We have put 2 new nuclear plants on of the advanced passively safe types in the past 2 years, but none are planned that I'm aware of. So why should we consider nuclear? My main reason is because it's the brightest hope for mitigating the electrical generation emissions that contribute to climate change. in my view, and I've been involved in this for the past 15, 20 years, informally breeding, global heating is an existential threat. And I don't mean an existential threat through the re-election of politicians. I mean, really, it's a problem. There was an article in the paper last year, I think, pointed out that 4 of the 5 planetary extinctions, all life, were caused by global heating. In that case, it was the emissions from volcanoes which caused the heating, and when that happens, various chemical reactions happen, and the seawater becomes saturated with sulfur dioxide instead of oxygen, and it all goes downhill for those of us who are there. So that isn't anywhere near, but all of those extinctions happened after the CO2 level reached 900 parts per million. It's currently over 400, and at the rate it's rising, it'll be less than 200 years to reach 900. Doesn't mean we'll have a planetary extinction, but it does mean it's more serious than probably most people have realized. 25% of our greenhouse gas emissions are from the electricity sector. I already noted nuclear provides most of it, but the others contribute also. It's safe. I don't expect you to believe me. You shouldn't believe me, actually, if I just tell you something like that. But I hope to show that studies prove that it's true. But it has risks along with the benefits. One thing to keep in mind, it's not nuclear or no nuclear. No nukes is a choice. It doesn't just stop there. What do you use? Here is the start of the safety argument. Hope you can read this, but let me bring it down. This is a EU study, European Union study, and what they did is determine the death rate from accidents and air pollution for the whole fuel cycle, that is from mining through operation of these various technologies. And no surprise, coal is the most dangerous, 24.6 deaths per terawatt hour, that's 1 billion kilowatt hours generated, which is the annual electricity consumption of 150,000 people in the EU. That's how they chose to measure this. Oil also up there, natural gas is much lower. Hydropower, wind, nuclear, and solar in the category of emissions free, and of those, wind, nuclear, and solar are very close and minuscule in impact. This includes any deaths from Fukushima or Chernobyl. There were no deaths from 3 Mile Island, and I'll get into those accidents, which we all know about, in a moment. Greenhouse gas emissions. This is a chart showing the emissions measured in CO2 per gigawatt hour, which is 1 million kilowatt hours, which is the annual electricity consumption of 150 people in the EU. Someone really liked the number 150. Again, coal is the worst offender, oil, natural gas, and nuclear is actually the best in this category. Surprisingly, solar, surprising to me anyway, solar comes out the highest among the emissions-free sources. That's because of the chemicals and the waste produced by solar energy. And we'll get into a little bit more of that in a moment. So again, the fossil fuels are the big offenders. No surprise, I was a little bit surprised at how the renewables fared, but nuclear energy, which is what we're talking about today, comes off well. Another category here that's very important in nuclear power generation is reliability. And the way this is traditionally measured is by capacity factor. For example, if a plant operates for a year, operates 100% of that time at 100% power, rated output, it has 100% capacity factor. As these statistics show, and these are US statistics, not EU statistics, nuclear has by far the best capacity factor of any of them. It wasn't always that way, but over the year we figured out how to get it right. And so 92.5% is good. Then you can you read the other numbers?
Yes.
Okay, so I won't go through them all. But one thing we have to note is wind and solar, because wind doesn't blow all the time and gets dark part of the time, they have a relatively low capacity factor. What that means is, when someone tells you they've just installed 90 megawatts of wind capacity off East Hampton, think 30. Because it's only operating at a 35% capacity factor if it makes the average. So, and it only lasts 20, 25 years. Nuclear plants last 60 years or more. So it's very difficult to make economic comparisons between these power sources. And I haven't done that in this presentation. It's really apples and watermelons. But it's worth noting that reliability is important. So why don't we use just solar and wind instead of nuclear? Nobody likes nuclear. That isn't true, of course, because 57% of the people polled last year in the US wanted to see more nuclear plants. Surprise. Anyway, the reason we can't rely on solar and wind is because they are potentially unavailable when they're needed. When the wind's, the other sources, fossil fuels, nuclear, are what the utilities call dispatchable. So when we need more input to the grid to meet the demand, the guy who handles that in the transmission department calls the right plants up and says, jack up your power level, because the demand is going up. And they can do it. Whereas the wind power and solar power are a function of Mother Nature. She decides when you can do that. And the result is it's not necessarily available when it's needed. So what we do now, when we have that situation, or what the dispatcher does, is he gets the backup power from fossil fuels. So if I'm going to build a wind farm or a solar farm, I have to have backup available already. That isn't counted in the price, but it has to be there, otherwise we don't have electricity when we need it. Or if you build either of the renewables, big farm, so to speak, you need a very large amount of energy storage, prohibitively large. And we don't have energy storage built into these plants. They will say, I had an experience here on the sustainability committee where I asked the salesman from South Fork Wind several years ago, they have battery storage, and I said, what is your energy storage capacity? He never answered. They say they have 90 megawatts of battery storage. What they don't tell you is megawatts is not a measure of storage. It's megawatt hours. So for how long will the battery last? A few seconds, minutes? Those batteries are designed to level the production. So if you get a gust of wind or falling off or whatever, the battery will kick in for a few seconds, maybe a few minutes. It'll hold the output steady. When I worked on a coal plant in Louisiana, I think the state law there was you had to have 30 days of coal storage. Dirty as hell, but it was there if for some reason the traffic on the Mississippi stopped and you didn't get your coal barge down when you needed it. And of course nuclear, the storage is built into the fuel. So looking at this and capacity factors and the fact that sun and wind by their very nature are weak energy sources, there's a lot of solar energy falling on the earth, but it's not dense. If it were dense, we'd all be crispy critters. And because of that, you need a large area for these facilities. The bottom line there, I found in one study, output of one average size nuclear reactor, which is about 900 megawatts, equals 8.5 million solar panels or 800 wind turbines. If you laid out a map of Long Island about like this, you'd see that. You'd see a little block like this. And of course, that energy is only available when Mother Nature decides it's available. I sound overly critical of these, I'm not. I have photovoltaic panels in my behind our barn. They've been great, no maintenance, saved us a lot of money. But I can't count on them. I have to count on the utility having backup power. So, one of the sources of power, as we know, is nuclear power. So, how does it work? This will be short. Here is a famous reactor site, which happens to be on an island in a river in Pennsylvania. Which nuclear site do you suppose that is? That's 3 Mile Island, where the accident happened in 1979. It is typical. So I've shown the cylindrical concrete buildings. There are 2 units on that site, and those are the reactor containment buildings. In a moment, I'll tell you schematically what's inside them. Other buildings, and let's see if this works. That building is where the turbine generator and the machinery that supplies the electricity is located. These are all backup structures. These 2 towers, which everyone sees most prominently, are not just for nuclear plants. All new plants generally have those cooling towers. They're to cool, take the waste heat out from the steam cycle. There's no radioactivity coming out or going into those facilities. But they're very prominent, everyone sees them. Inside the reactor containment building, I'll walk away from the microphone. Here's the fuel. There are about 20 million fuel pellets, not like that, which are made of ceramic. Inside them is the fuel. They are stacked in fuel rods about like that, just slightly bigger than the pellets. And that's what generates the heat. Fission of the uranium oxide in those fuel pellets generates the nuclear heat. the way it's removed from the reactor and eventually ends up in the turbine generator is high pressure water, 2,250 pounds per square inch, 600 degrees. This water, because it's under high pressure, is circulated through the reactor, then through tubes in what's called a steam generator. On the other side of the tubes is regular water. The heat from the tubes boils the water, creates steam, which goes into the turbine generator and runs the turbine and runs the generator. That generates the electricity. In principle, it's very simple. In practice, of course, a bit about the most complicated part of the plant is generally this part. But the one that people worry about the most, of course, since 10 million accidents, because radiation is involved, is this one. So that's how it works in simple terms, but it is fundamentally simple. The fission boils the water, creates the steam, goes through the turbine. We generate electricity with it. The risks of nuclear power have to do with radiation. These are some just facts of which you're probably aware, but radiation occurs naturally. It's generated by decay, radioactive decay in uranium, which is found in the earth. It comes down from the sun in the form of cosmic rays. We get about 0.36 or 360 milligrams per year from natural causes, of which part of that is medical x-rays, things like that. They give you radiation also. The radiation, if it's too much, or if it gets to the wrong places, like breathe in a radioactive isotope, plutonium, for example. You can hold plutonium in your hand and it won't hurt you. But if it oxidizes, becomes dust, then you breathe it in, then because your lung tissues are so sensitive, it can cause cancer. Probably would cause cancer. And the same thing is true if you ingest radioactive isotopes. Your insides are sensitive to that, and you're more likely to develop cancer. Not from the direct dose to the outside of your body, but from the inside. The public, of course, gets, I shouldn't say of course, the public does get essentially unmeasurably small amounts of radiation from a nuclear power plant. I say unmeasurably literally because you really can't tell. You can't measure it. It's too small at the site boundary. And of course, the good thing about radiation is it can cure cancer if used properly, and it decays with time. And the radioactive isotopes, they may decay in seconds, which usually means that they decay with a high output of energy. They're high dose radioisotopes. Or it can take hundreds of thousands of years. In the case of uranium, for example, which gives off very low dose. That correlation, if it has a short half-life, it's high dose, and the reverse, if it's low dose, is, I don't know of any exceptions to it. What the decay time is measured was termed half-life. That's as long as it takes for the isotope to decay in dose by half. So that's the way it works. We don't see any difference in radiation caused cancers or such things between Denver and New York. So even though Denver has about twice the natural radiation, it's higher in elevation. So some people have concluded, I met one years ago in Japan, a scientist, who concluded that they support the hormesis theory, which is that a small amount of radiation is actually good for you because it stimulates the, what do you call it, when your natural reaction is stimulated by a small amount of radiation, and it increases the activity in your immune system. I don't know whether it's true or not. These people are not stupid. And it would seem to be supported in my mind by the fact that variations in naturally occurring radiation up to a certain point don't seem to be reflected in cancer data. But importantly, how have we done in the nuclear industry by protecting our workers and the outside people from radiation? Well, over the years, the latest one I found was 2015, but there may be others. It takes years to do an epidemiology study because you basically have to have not only the dose rates in given areas, but the cancer incidence. And you put those two together with, commonly they do it with adjacent counties. You pick a county where there's a nuclear power plant, and then you compare the cancer rate in that county with the cancer rate in adjacent counties, which may be basically the same from the environmental standpoint, but the difference being they don't have a good power plant. What those reports have shown, and there are always some, gee, this data was a little off, but we think it's because of that, which has nothing to do with the nuclear power plant. They all show consistently no increase in cancers in those areas where you have nuclear power plants. So, to me, that's particularly important. I'm going to skip this because I want to have enough time for questions. So let's talk about nuclear accidents. The first one, major one, was 3 Mile Island in 1979. I was there after the accident as part of the recovery team, so I know something about it. I was there for several weeks and accumulated no radiation, according to my dosimeter. But this was a bad accident, not just because it wrecked the plant and disrupted many people's lives, but because it was caused by the operators. A relief valve lifted due to a series of mistakes that were made on the steam plant side. The load that the reactor was supplying, it was at 97% power at that time, immediately was shut off. So the reactor, it has inertia. It kept, even though the proper controls worked, it kept generating power for a while, and the operator, and it lifted a relief valve in the pressurizer, which was on another tank, and the valve didn't recede. The operators didn't know that it had receded. They could have. It wasn't made easy for them in the control system to know this. But anyway, so primary coolant was discharged for a couple of hours into the reactor building basement, and eventually overflowed into the auxiliary building. And the operators, because they didn't know what was going on, they shut down a key automatic system that would have kept water in the reactor. So it all happened not the way it was supposed to happen. I recall one night I was walking between our trailer and the containment building, and I met their vice president of operation. He was just on the path. And we just sort of shook our heads. That kind of thing's not supposed to happen. But it did happen. So people weren't injured because of it, according to the Pennsylvania Department of Health and various studies they've done and other people have done. They could have been. And so that can't happen again. You don't want to. The aftermath. The public was protected. What we call defense in depth, which is redundant safety systems, redundant inspections, etc. It worked mainly because we had a containment building, which is the ultimate barrier between radiation released and public. I think that's important when we come to the next accident I'm going to tell you about. And it was a wake-up call to the industry. It was a wake-up call to the Nuclear Regulatory Commission. Big changes were made. Now, every nuclear plant has to have a full-scale simulator, which is a giant electronic mock-up of the control room so the operators can practice. They're fed, this is happening, this is happening. What do you do? And it's great training. There was a new industry oversight organization formed. It wasn't government, it was formed by the utilities. It was called the Institute of Nuclear Power Operation, and it was staffed by very experienced, primarily former submarine commanders. Now, as some of you may know, most of our reactors are in the naval nuclear propulsion forces, powering aircraft carriers and submarines. I worked there for 15 years, was responsible for the 688 class submarines and the little submarine. And so those guys are good, and they don't have any profit motive. And there were more inspections put in, there were more safety devices, et cetera, et cetera. So it was useful in that sense. Chernobyl, a different cause, although the operators were involved. Worse accident, the worst of the three by far, because people were killed and they died trying to keep the reactor radioactivity contained. What happened was the reactor design was fundamentally unsafe. From a physics standpoint, reactors in this country and in Europe are designed so that when the temperature in the coolant goes up, the reactor power automatically goes down. You still may have to move the control rods to control it, but that's called a negative power coefficient. In the case of Chernobyl, because of its physics design, during the startup phase, there was a period where if the reactor water heated up, the power went up. Exactly the opposite of what you want. And then that's a recipe for disaster. Anyway, they did. And of course, the disaster happened. The reactor ran away during the startup phase, and because there was no containment building, and when the reactor blew up, not nuclear explosion, but because of all the heat quickly put into the coolant, there was a steam explosion. Blew the top off the reactor, leaving it exposed to the air. It had carbon moderator in it, which is, I won't bother with the technical details, but carbon burns when it's hot and exposed to the air. So you had a fire, you had a release of the fission products because all the fuel was destroyed in the explosion. And you had people in helicopters trying to put out the fire by hovering above an open reactor vessel and dumping things into it. Very brave people. All right. The consequences of that, according to the reports from the World Health Organization, 263 dead, potentially thousands of others. I say potentially because studies are trying to predict something here which They aren't necessarily very good at predicting. Due to cancer, there has been a significant increase in child thyroid cancer, and a huge amount of land was contaminated, and people, of course, were evacuated. This was, we call it Russian reactor. It was a Russian-designed reactor. It was located in Ukraine, which was at that time part of the Soviet Union. Needless to say, the Russians no longer design reactors without containment. Finally, Fukushima, which is the most recent in Japan. This is a boiling water reactor, not pressurized. The water that's in the reactor is actually boiled and goes directly to the turbine generator. There are, I don't know, 30 or 40 of these in the world. It's a GE design. And when they started out, the pressurized water reactors and the boiling water reactors were competing directly for business. There are more pressurized water reactors than boiling water reactors. Anyway, there was a severe earthquake, different cause. The earthquake didn't harm the reactor as best anyone can tell. What did, of course, is the tsunami that happened as a result of the earthquake offshore. The tsunami was twice as high as the retaining wall that was designed to protect the reactor site from such an event. So when the tsunami topped the retaining wall, it also destroyed the emergency power sources. Now, backing up a little bit, when the earthquake happened, all of the electricity sources in Fukushima and that whole area went down. The reactor automatically scrammed, but all their other sources too, the transmission lines were out, etc. So the only source of emergency power to remove what is called decay heat from the reactor, which means that when the reactor shuts down, it's still generating some heat from radioactive decay of what's in the reactor fuel. And that decays to essentially nothing, but it takes weeks for that to happen. So all reactors of that type, all reactors except the kind I'm just going to mention, need auxiliary power to keep them safe. That's why they all have at least 2 diesel generators that are designed to provide that power. But when the tidal wave came over the wall, the water went into the basement, which is where the diesel generators were. So that was the safest place for the diesel generators from the standpoint of an earthquake. But from the standpoint of flooding, of course, it was the worst possible place. And so they had no emergency power. The result was eventually the reactor fuel overheated and fission products were released into their emergency containment, but it overpressurized it, so it had to be vented to the outside world. So there was some release of radioactivity. It was worse than 3 Mile Island, not nearly as bad as Chernobyl from the standpoint of human health, but terrible from the standpoint of the amount of the area that had to be evacuated. There was 1 death from a radiation worker. I think it was the head of the plant. I didn't have time to confirm this, who absorbed too much radiation. He was doing his inspections. 2,000 plus people died because of the evacuation. I'm not criticizing the fact that they ordered an evacuation. They probably couldn't have done anything else. But due to traffic accidents and stress and heart attacks over a period of weeks, it took its toll. The workers received a high level of radiation, but as I said, that was 7 years ago so far. Only 1 person has died. And the UN committee, Scientific Committee on the Effects of Atomic Radiation, conclude from their studies that there's no increased risk of cancer because the dose rates that the public had were not high. But it was obviously a terrible thing that affects the whole area today. So how do we not do this again? I mean, that's 3 accidents in thousands of years of reactor years of operation. In a normal industrial setting, that's a sterling safety record. But given the potential impact on the surroundings, that's not sterling enough. So what we started, and the nuclear industry started doing years ago, was to design reactors that didn't need emergency power after they shut down. They have natural circulation, valves that fail open, and a big tank of water on the roof of the containment building, which cools and boils and the heat is removed, all without the use of electricity. So for 72 hours after an accident like that happens, you don't have to do anything, but at the end of 72 hours, you have to fill the tank, which is on the roof, literally on the roof of the containment building. So this is called passively safe reactors. And in my view, both the TMI and the Fukushima accidents could have been avoided if this type of reactor design were used. It is being used now. The latest 2 reactors that were brought online in this country and 4 that were recently brought online in China are all of this design. However, I don't think there's any requirement that it be done. I can't see anything else being built in this country other than a passively safe reactor. I don't know about the Chinese, and they're building more than anybody. So I think we could have avoided the accidents. There's no question that the Achilles heel of the earlier nuclear power plant designs is this need for a backup source of electricity. For example, Shoreham, it had 5 diesel generators. It was probably going to be the safest reactor in the country. But anyway, enough on that. How are we doing? This is the last topic. Everyone's favorite. Spent nuclear fuel is what high-level waste is. That's basically the definition of it. And right now, spent nuclear fuel is taken from the reactor every 2 years is a complete cycle. It's put in fuel pools, such as the one on the lower right, and allowed to cool. Water is circulated through the pool, and eventually the decay heat stops or to a level where it doesn't need warm circulation anymore. Then the spent fuel is moved to the cask, or like those in the upper right, which are casks made of stainless steel and surrounded by reinforced concrete and inerted with helium. The NRC has told us, let's see, I think they're good for 120 years. And that's probably a lot longer. But this is where the radioactive waste is now stored, at each power plant or nuclear facility. Is it safe? Yeah, I think it's a lot safer than burying it myself. But it is stored that way, and that's the plan for the foreseeable future. Transportation is handled if it has to be transported, say, to another site. It's in this monstrous thing, which we probably think of that will show. Those big discs on either end are compression absorbing discs. So they travel by train mainly. If there were to be a train accident, the analyses show these would be just fine. Whatever they hit would not be. So, one thing, final fact about radioactive waste, which is very important. The spent fuel in those casks has 90% of its usable fuel still there. When the reactor fuel is spent, so to speak, what that means is there are enough nuclear poisons, neutron absorbers that don't fission, created in the fuel that you can't make the reactor go critical anymore. Also, the reactor, the neutrons in the fission process, they don't all go to creating a chain reaction. Many of them end up being absorbed by the uranium-238 and creating plutonium-239. A third of the energy supplied by a reactor is from the plutonium that's generated by the reactor itself. There's a lot of that plutonium left. It's perfectly fissionable. The Europeans, for example, the Europeans right now use what's called mixed oxide fuel. Not in all their reactors, but in many. It's a mixture of plutonium oxide and uranium oxide. They recycle, reprocess chemically their spent fuel, remove the plutonium, and make new fuel with it. And you can burn that in existing reactors. And therefore, you don't have to store it for tens of thousands of years. You destroy it usefully, getting 200 times as much energy from the original uranium than you would otherwise. So this is important from both the standpoint of energy and efficiency in use of uranium and waste disposal. Because the problem with waste disposal is long-term, long half-life isotopes like plutonium. The fission products that are in spent fuel are an average of 30-year half-life. I once testified to Congress on a program that was designed to take advantage of this. And the senator, when I told him that if you remove the fission products, then what's left, if you remove the plutonium, then what's left, the fission products, can either be used for medical uses or other uses, or they can be buried. And in about 300 or 400 years, they will have decayed to more or less background. Now, Southampton is 300 and some years old. So are we saying that's too difficult? No, it's not too difficult. But if you say to someone, I'm going to store the plutonium underground for 10,000 years, which would not be enough to make it background, by the way, I would be the first person to raise my hand and say that's nonsense. We can't do that. However, recycling the fuel requires that there is some free plutonium in the process. It's available. And so President Carter, back when he was president, he canceled the program because his staff urged him to think of it as a proliferation threat. The rest of the world doesn't think of it that way. The rest of the world thinks of it as an energy source. So what have we done? In 1987, we were ordered to bury the spent nuclear fuel at Yucca Mountain in Nevada. In 2000, and that went on, we spent $10 to $13 billion. Not finished, but it was being licensed by the NRC. Then in 2009, in the midst of a very difficult election for Senator Harry Reid, his mentor and the majority leader in the Senate, he abruptly withdrew the application to Yucca Mountain, ordered a blue ribbon panel to look at it. They did, of course, what all blue ribbon panels do. They had a bunch of generalized recommendations, which have accomplished nothing. And we're back where we started. Fortunately, where we are storing it, as I pointed out earlier, is safe. It's safe for decades yet. We've got time to figure it out, and hopefully time to get people in charge who have the guts to make the right decisions. So current, we don't have a long-term solution in place. Most of the rest of the world looks forward to eventual burial. Finland actually has its closest to have an operating burial site. But we have to get one. But it's not an emergency. The emergency is climate change. So, as I say, my recommendation is to recycle it, do what the Europeans are doing, take advantage of the energy, store the remaining material above ground so that it's available for medical uses and other uses, which haven't even been thought about yet. In conclusion, I believe nuclear power has demonstrated that it is a safe, reliable source of emissions-free electricity. The passively safe designs that are currently available and being built make it even better. Nuclear waste is a political problem with a technical solution. And so we have time to convince people or find another solution. We need reliable, emissions-free electrical generation to combat global heating. This should include nuclear and renewables and any other brilliant idea that people come up with. The problem is doing it in an emissions-free way. If we know how to do it, let's get on. Questions? Peter?
Thank you very much for this comprehensive demonstration for nuclear. The problem I see is to build a new nuclear facility takes, what, 10 years? The timing is horrible. To replace, that's why we are building wind, solar, etc. to do something.
We're building a fruit to take the place of a vegetable. The problem is that wind and solar renewables can't take the place of baseload electricity, and eventually, the sources that we have now, and eventually people will figure that out. The New York State, NYSERDA, New York State Energy Research and Development Administration or agency, they still don't quote battery storage in energy storage terms. I wrote them a letter, ignored it. We are, I'm afraid, being a little bit hoodwinked here. But nuclear power plants do cost too much and take too long to build here. In China, they build them in 6 years. Same plant. So I think our problem is we need to look at just what kind of bureaucracy we've put in the way of building these plants. The company I worked for 13 years, which was the architect engineer on 3 Mile Island, they were the architect engineer on the first commercial nuclear power plant of any size, Oyster Creek in New Jersey. Their contract, this is laughable, of course it was in the 60s, but still, was $5 million. They lost their shirt on it, but I was responsible for 2 nuclear plant designs as the project manager for the same company. Our contracts would have been a couple $100 million. Plus, we didn't, I should say, at that point have standardized designs. In the Navy Nuclear Propulsion Program, we had standard designs. For a given class of ships, you get this reactor. Cookie cutter. They're still expensive, but that was what standardization and mass production is supposed to be able to do. In France, they did something similar. France has one utility. We have 2,000. Each one of them is the customer. Now, they can't all afford nuclear power plants, but, and each one of them wants something just like what they had before, except it's nuclear power. Forget it. You know, it just won't work. We all knew it wouldn't work. We took their money anyway, because they're the customer. So what we need to do, and during this period, when I eventually ended up at the Department of Energy, responsible for the Office of Nuclear Energy. And what we have worked out with civilian nuclear industry is standardized designs. The AB 1000 that I mentioned are being built now, and it's basically the same thing. They're a standardized design. What that means is you present all your drawings, and et cetera, your technical details to the Nuclear Regulatory Commission before you commit to build the plant. So you've invested money, maybe a couple $100 million, but you haven't invested billions of dollars. So you do that, they have eventually approved them. Now, if some utility wants one, they have to buy that design. And eventually, if we ever get back to building them in large numbers, we will have the ability to do more of a cookie cutter approach. And our costs will come down, and people will get back into the industry who will learn how to build again.
Question, how long do the, I guess it depends on how, but how long do the rods last? And how much supply do we have for the nuclear fuel? Is it, and do we manufacture locally, or do we have to import it from other countries?
The rods, the average reactor core lasts about 2 years. In an aircraft carrier, it lasts 30 years. It just depends on how you design it and how much it costs initially versus later. We make our own fuel. We have our own uranium supplies, but for many years, for replacement fuel for our existing reactors, we used diluted Russian weapons-grade fuel. Because as part of the, what was it called, the treaty where we all brought our nuclear weapons down, a lot of fissionable material became available. And the Russians couldn't use it all, so we bought it. Unfortunately, that meant we shut down our own facilities for enriching fuel. So eventually, soon, I think, we're going to run out of Russian fuel. So we have to build an industry again. We had one. We didn't run it quite right. And now we have to build it again if we're going to be serious about this. Yes?
What would the most effective way for the public to give input so this can be acted?
I think writing to the Department of Energy indicating your support, writing the Sierra Club saying get off your high horse and stop bad-mouthing nuclear power. The Sierra Club has in their charter that they're opposed to nuclear power forever. It's insane. And the environmental, there's a herd instinct in all industries, and it certainly exists in the environmental movement. In fact, years ago, I sponsored a conference where I brought together Greenpeace and Westinghouse and GE, and all the guys, you know, I was sort of hoping naively, we just all get in a room and start talking, and you know, it'd be like gossip free. Well, it obviously didn't happen that way. But when I had lunch with one of the guys who worked for, I think it was NRDC, and I mentioned this, he said, we all know, we environmentalists, all know that we need nuclear power. This was in the early 90s. But we can't advocate for it because they work for someone. it's not just industry people who work for someone. The anti-nukes and environmentalists, they work for people too. And so that was actually the most beneficial thing that came out of the conference, as far as I was concerned. But we have to change the attitudes, and if the public, as I mentioned, let's see, just quickly. This is what the public thinks about nuclear power. This is as of last June. U.S. adults, 57% favor more nuclear power. It's always been quite high. A pollster called me when I was in DOE, as participated in a poll on like this. And after he was finished asking me his questions, I asked him, I said, what have you found? And he had been polling congressmen, industry leaders like me, and he asked a third question. The Congress, which I'll tell you in a minute, the Congress people and the industry people and the public were all together. At that time, it was even higher than 57% more nuclear power plants. Then he said, but when I asked the congressmen what they thought the people wanted, it flipped. And the reason it flipped is because the most effective lobby in this area are the environmentalists and the anti-nukes. They're very powerful in Congress. So congressmen believed what they were being told. I think that's changing now. Both the Trump administration and the Biden administration are much more positive and providing much more in resource to the nuclear industry and for nuclear plants. You don't hear the anti-nuke rhetoric that you heard from the Clinton administration when I was struggling to get anything in my budget. So it's changing, but it needs to change much faster. And Dieter's right. The biggest problem we have is cost, which is related, of course, to time to build. I don't have a cost slide up here for the reasons I said. You can't compare apples and oranges or watermelons. So, but we do need to, if you believe what I've told you, we need to support it and let the politicians know that we do support it. I'm being told to move on. I'm my wife.
Two-part question. I thought I had read that newer designs of nuclear reactors were far more efficient, so there was less waste than in the older plants. I don't know if that's true. And also I'd read about smaller, more decentralized reactors.
Small modular reactors. Yeah, the small modular reactors, the way the industry is currently attacking the cost problem, at least in this country, is to build smaller plants. And they will be cheaper in capital costs in particular, and they want to make them so they can be mass pieces, hence the term modular, can be produced in factories, shipped by rail, all plugged in, and it'll build faster. It all sounds great. The first ones aren't going to be cheaper because they'll be the first ones. And we have to get over this idea that, gee, we can't afford to do the right thing, even if we believe that in the long term, it'll be cheaper. But the reason nuclear plants are 1,200 megawatts instead of the 300 that they're talking about for modular reactors is because the electricity is cheaper with the economies of scale. Not if you don't standardize, however. If every plant you build is effectively number one of that plant, then you never get the economies of scale and it costs. So they'll proceed, and the small modular reactors, they should be easier to build, actually. And we'll see. The market will do so.
What about the storage?
I'm not aware that,
Or efficiency?
yeah, I'm not aware of less waste, other than if you reprocess the spent fuel, there will be less waste, but I don't see that. That's politically still, I think, being killed by the concerns about proliferation or whatever. So I don't know about
Okay.
that. Yes?
Most of the power plants, and most of the nuclear plants in the country were built in the 70s, so I've been in a couple of them, and my son worked for one.
Mhm.
The technology is old,
Yeah.
and I know there's no effort to like upgrade the technology, so does that hinder the safety?
Well, there actually is the effort to upgrade the technology, and that's by these new standard passively safe designs. And the last two plants built in this country, which went online this year, I think this year or late last year, and the year before, Plant Vogel in Georgia, are of this new design. They didn't just put in passive safety systems. What they did is design the plants so they had fewer components. They'd use the latest electronics. So everything would be perfectly new and modern. But whether
The old ones, my question
Yeah.
really is, the old ones aren't.
the old ones are upgraded periodically, and for example, the original plants were licensed for 20 years in the beginning, then 30 years, then 40 years. And as part of the extension of life, the reason nuclear power still provides 20% of our electricity is because many of the plants have been extended in their life, which cost several $100 million to modernize the plant. And you can do this with everything except the reactor vessel probably, which doesn't need modernization. So yeah, there is effort to do that. And the plant operators, utilities, have to meet current NRC requirements. So is it as good as a new plant designed from scratch? Maybe not, maybe yes. Because new plants designed from scratch still have a learning curve to go through.
Another question, is there any possibility that the existing plants can be retrofitted with the passive water system?
Not really.
No, it just is.
They're so different.
You say that we have time, but it seems to me that it's a race.
No, I didn't. Well, if I left you the impression I thought we had time, I misspoke. I don't think we have time. I think climate change is here, and we need to move as quickly as we can. And I'm not sanguine about the probability that happened.
I should probably know this already, but it sticks in my mind. We're in a paranoid times. It's a paranoid question. If there's a plant and somebody wants to bomb it, or sabotage, or a suicide kind of thing, or earthquake, I mean real serious earthquake, then what happens to the
To the current ones?
well, the ones, if there were a new one built to the best standards, what
Well,
would
this-
happen to it in those various cases?
The standards of the new plants and the old plants, from the standpoint of responding to terrorist attack, that kind of thing, they aren't really different. You have to be, capable of repelling borders, so to speak. And there are extensive classified security plans for the plants to prevent this. Bombing a nuclear plant would be a sure way to waste explosives. I mean, the containment building is 3 feet thick of reinforced concrete, highly reinforced concrete. So they're designed to withstand the impact of large jet planes. I'm not saying it'd be impossible. That's not a particularly viable target.
There is a nuclear plant in the Ukraine that was in the middle of a war zone.
Yeah,
How
and
dangerous is
it's,
that?
it still is in the middle of a war zone. The Russians occupied it, then the Ukrainians took it back when the Russians withdrew. And there were a lot of worried people, particularly from the United Nations and the International Atomic Energy Agency, etc. There was no release. Apparently the plant wasn't damaged in any critical way. But yes, it can happen. I mean, it's not the only thing that can cause mass casualties. That probably would be less likely to cause it than if you attacked a chemical plant and released everything there, because it has no protection from the outside. But it's bad in case. Okay? Thank you.